I've been working at WhatsApp, as mentioned, from 6 years ago when I was an intern, and I've been there full-time for 4 years. There's been a lot of discussion about distributed consensus and distributed computation these past 2 days, and I'm really excited to be presenting Raft here. Raft got its jump start at WhatsApp, 6 years ago when College Me worked with one of the engineers there on a Erlang implementation of it, very bare bones Erlang implementation. Over the years, and with a lot of added elbow grease and aspirations, it now powers our message database. And every moment it's hard at work, powering our message delivery and preventing message loss for billions of users. In this talk, I'll briefly describe the consensus problem. Then I'll discuss the approach that Raft takes to solving it. And then I will detail some ways we took Raft for use at scale at WhatsApp. So let's get started. So consensus, we've heard that word a lot these past 2 days. What is consensus? Briefly put, in distributed computing, consensus is just the problem of getting machines to agree with one another. In yesterday's keynote, there was a mention about all of the different types of flavors of consensus we might get. It's a very good talk. The difficult part of consensus is that oftentimes you don't know anything about the machines that you want to communicate. These machines could be anywhere in the world. They might not know anything about themselves, like not even what time it is. And they could even have failing hardware. Consensus algorithms are designed to help us get these machines to work together regardless. The Raft algorithm is one of the many approaches to the consensus problem. It is using a few technical terms, and I'll talk about these technical terms in this presentation, a distributed consensus algorithm for state machine replication. So what is a state machine? Here I'll introduce state machine as a way to model a database. It is much more general than that, but I'll keep it at that. First, at the core of every state machine is a transition function. For a database, you'd really like your transition function to be implemented in code. Now, the transition function takes a state and an input. And here I have a state with A is equal to 1, B is 2, and C is 3, very simple. And an input in which we want to set B to be 4. With the starting state and input, we can give them to the transition function, and then B, we can see here that afterwards B is set to 4. For a database, we might want the transition function to take all of the inputs or all the changes we might want to make to our database. We can take each change and pass it to the transition function one after another, and this creates a sequence of operations that models the way we might use our database. In Raft, the sequence of operations is called the log. You can think of it as this logbook that lists every change we've ever made to the database. Each individual operation in our log is a log entry. So if our transition function always produces the same result every time we give it the same state and the same operation, then the log is very convenient. Because if I want to get the state of the database at a certain period of time, all I need is the log up to that point in time. I just take all the operations in my log, put it into my transition function, and out will come my final state. So we have a state machine. We can put it on all of our machines. Now, how do we get the log to each of our machines? Raft has the answer. Raft and many other consensus algorithms rely on a very simple mathematical property. Suppose that we have this cluster of 5 members. Notice I've circled an absolute majority here. I can't make another absolute majority with the 2 remaining members. Of course, this holds for any size cluster, not just 5. It works for 3, 4, 5, 6, 7. Raft also doesn't care if it's just... Raft also isn't limited to just clusters of 5. I'm just using 5 here as an example. To achieve consensus, when we ask a question to the cluster, we need some way for the cluster to agree on an answer. If we limit the types of questions we can ask to questions about agreeing or disagreeing to something, then we can let all the members in the cluster vote about whether they agree or disagree. And the absolute majority, or the uniqueness of the absolute majority, ensures that the cluster can only agree or disagree as a whole. This leads to the concept of a quorum. A quorum is just an absolute majority of our cluster that has agreed to something. And all we need is for the members of our cluster to agree. Once they've agreed, they've created a quorum, even if nobody knows who agreed or disagreed. Now, the fact that we want to agree on in Raft is the log, or specifically a prefix of the log. And a prefix is just the continuous section of a log that starts from the very start of history. Whenever we have new things to add to the log or new log entries to add, Raft will ask the cluster whether it agrees to adding something to the log. Raft guarantees that once we have agreed on a portion of the log, it will not change it ever again. So, if we want to make progress, Raft needs to be able to accept new log entries. At the same time, it needs to make sure that existing quorum or existing log entries we've agreed on are preserved. So, Raft divides the cluster into leaders and followers. When a cluster is operating normally, there is only one leader. Here the leader is at the top, and I've marked it with an L. All other members of the cluster are called followers, and I've marked them here with an F. Each member of the cluster will also have its own copy of the log. Every so often, the leader will send a message to each of the followers. This is called the heartbeat. The leader will include a portion of the log that each follower is missing so that it can update followers on this. When each follower gets the heartbeat, it'll check its own log, decide whether or not it agrees with the leader. If it does, basically if the log entries match, then it will add the new log entries to its own log and record this and say, I agree. If the follower's log entries don't match, then the follower will delete its own log entries because they aren't correct anymore and disagree with the leader. For the disagreeing follower, the leader will work with the disagreeing follower later on to try to find some portion of the log that it does agree with. If the heartbeat is successful, then the follower will say, everything is good, I agree. If the heartbeat is unsuccessful, then the follower will tell the leader that I did not make any progress at this time. Now, the leader gets this information from all the followers, and it can figure out who now has which log entries. And it can calculate the quorum that has been established across our cluster. Once a quorum has been established, in Raft we call these log entries committed, and they can never be changed again. In the next heartbeat, the leader will tell all the followers which log entries have been committed so that all of the followers know. Now that everybody knows, each of the members of our cluster can know which log entries they can use, which ones are in the quorum, and that these log entries will never change in the future. The real world is not as pretty as this, though. I haven't covered what happens if some of the nodes fail. Raft relies on there being a functional leader, one that can send and receive messages from the rest of the cluster to make progress. It's impractical to assume that all of our members will never fail. So to be able to ensure quorum even when nodes fail, Raft also defines a careful way to replace a failing leader. First, Raft will need to divide time into multiple terms. And these terms, of course, it's a confusing term because Erlang uses term to mean something completely different. But here, term means an arbitrary period of time, and it's identified by a number that always increases. You can see here that I've added a number to each of these members, so they're part of term 5 right now. Every time a message is sent in a Raft cluster, we include the term. If I get a message from an older term, I just ignore it because it's no longer relevant. And if I get a message with a newer term, then I will move to that term by setting the term that I know about to the newer term. Here I have a failed leader, and everyone's in term 5. When the leader fails, now all of my followers are not getting heartbeats from the leader. All of the followers will likely notice this, but only one follower will be the first to decide that the leader has failed. This follower will try to start an election to replace the failed leader. First, it will advance its term by 1, so now it's in term 6, and it will become a candidate, and here labeled as C. The candidate will then request votes from everybody in the cluster, including itself. At this point, because every member of the cluster has gotten a message from term 6, they also move to term 6. Now, members will only grant its vote if the candidate's log is as up-to-date as its own. Here, all the functioning members do grant their vote because, as circled, this candidate is part of the most up-to-date quorum. And so it cannot be the case that the other logs are more up-to-date. Once the candidate discovers it has gotten the majority of votes, it has an election quorum, and it becomes leader. We always advance the term because we can only vote for one candidate each term. That way, we never elect multiple leaders. Now, it's very critical that we don't elect a candidate that's outside of our quorum, because this candidate might, if it becomes leader, might want to change an existing log entry. The election scheme requires that a candidate gets at least one vote from a member of the quorum, because otherwise it cannot get enough votes. In this example, I have this candidate that's not part of the most recent quorum attempt to run for leader. It cannot get votes from any of the members of the most up-to-date quorum because its log is out of date. It can only get a vote from its one sole peer here. So the election fails. After some additional time, the election is retried and one random follower will win the race to be the first to start the election. And hopefully this time one of these 3 wins that race. All right, I've covered 2 of the most important parts of Raft in this very oversimplified and incomplete summary of Raft. It's very complicated. So now we have some reliable log replication and a deterministic state machine. So those are the 2 parts we need to build a replicated database, or at least one type of replicated database. First, Raft guarantees that each copy of our database gets the same log. Then we put the same state machine on each of our logs, and we give the log to each of our state machines, and we end up with the same state on each machine. Nice, we've done it. So, that's a bunch of theory. How do we take Raft and scale it up to billions of users? There are lots of different ways to take Raft and make a database out of it, but I will mostly be talking about Wraft. Wraft is WhatsApp's implementation of Raft in Erlang, and I've been working on it for 4 years, basically. It's open source, and it's designed as a library geared towards the development of replicated databases. At its core, big diagram, While Raft uses a simple sharding strategy, like lots of databases, to distribute work across multiple Raft clusters. In Wild Raft, we provide the ability to start a number of instances under standard OTP supervision. Each instance of Wild Raft starts a collection of processes that together form a single member of the Raft cluster, and that person icon I had in that group of 5 earlier. If we distribute instances of raw Raft across multiple nodes and across multiple data centers, we can form Raft clusters, and most importantly, Raft clusters that are resilient against failure in a single location. Once started, Wild Raft takes over responsibility for all of the Raft communications. Now, at full speed, each of our Raft clusters can handle upwards of 1,000 log entries per second. Of course, this depends on how complicated your database is. At WhatsApp, we run up to 32 of these per node, so each cluster can handle tens of thousands of database requests. Distributed over thousands of clusters, distributing this across thousands of clusters allows us to handle upwards of 20 million database requests per second. So how does Wraft handle new log entries? So Wraft doesn't really know what your database wants. So first you have to make your API request into a log entry. But once you have that, you send it to the acceptor. The acceptor will store information about who requested it to a queue. We keep this queue in ets. If the queue is not full, then we send it to the Raft server. The Raft server is a GenStateM, and it implements the entire Raft algorithm. Usually you can only do operations against Raft on the leader, so if the server happens to be the leader, it will accept it. Otherwise, we reject it at this point. Now, the server will put the log entries into the log. Raft does not provide an implementation of how exactly to store log entries to disk. We probably could not do it as well as one of the local storage solutions out there. Now that it is on disk, the Raft server will replicate the log entry and wait for it to be committed. Once it's committed, it forwards this request to storage, which finally, the log entry has reached your state machine, and you can do the database-y things. We do not provide an implementation of the state machine because no two databases are identical. After the state machine produces the result, we remove the request from the queue, and you get a response. Of course, the followers will also execute the log entry against the state machine, but we don't do any verification here. Their results are just discarded. The core Raft algorithm is really good. It provides a great foundation for databases, but it doesn't describe every detail about how to make it performant. To push Raft further and further, we've made many adjustments and added ways to adjust details of the Raft implementation while developing Raft. These optimizations will fall into 3 categories, and I'll briefly go over them. First, pipelining and overall optimization allows us to increase the throughput of a single Raft cluster. One important thing that we do to handle more requests is to never block on an incoming log entry. You can see that all of the way that we handle log entries, none of our servers will wait for a single log entry to be processed before returning control. When the new log entry is handled by an acceptor, we just add it to a queue. When it is on the server, it goes into the log, and the server will handle it the next time there's a heartbeat. When it gets to storage, we ask the state machine to do the work and then pop it off the queue. None of our servers will ever block. Of course, there are some concerns here. What happens if the server is no longer the leader? Well, simple. We have to pop everything off the queue and tell you that we're no longer the leader, sorry. And then one other thing that you might notice is that we reply from storage, not from the acceptor. So if you're making a gen call to the acceptor, we may never know if the acceptor or if the storage server failed. All of these services are under a single supervisor with an all-for-one strategy. So if storage or the server or the queue or anything else fails, the acceptor will also exit, so you get notified. Another place where efficiency is very important is in the critical section. The critical section is the portion of the state machine that is actually performing, operating that's accepting your log entries and doing all the work. Raft requires that you perform Raft requires that log entries are processed by the state machine in strict order. This is where the consistency comes from. There's no possibility to provide parallelism at the critical section, so it's critical to ensure that log entries are processed as fast as possible so that you can get more out of your Raft cluster. The solution that WhatsApp adopted here is to use cache-style operations. What this means is that instead of reading data and computing the result from within the state machine, we pre-compute all of the data before we send the log entry to be replicated. To do this safely, we attach a version to all pieces of data. And when we access the data while pre-computing the changes, we store that and send these versions as part of the log entry and verify the versions attached with the data at the database when processing it. The key point is that cache operations can often remove portions of data that are duplicated in your request. This makes them cheaper to replicate and process. In many cases, if the operation is very simple, you can do things without even knowing the input data. Things like counters or flags can be manipulated without ever reading, and so can go through without any pre-processing. We also improve throughput through pipelining the log replication mechanism. Normally, as I described it earlier, the leader will send log entries to followers. Then followers will send the acknowledgement or rejection of these entries. However, this can be very slow if the leader and follower are very far apart. Instead, Raft will keep sending log entries as long as log entries are available, even without waiting for followers to acknowledge them. In the general case, the follower is actually keeping up with the leader just fine, and so this allows us to send more log entries. However, if there is replication failure, then the leader will get that information from the follower and can reset the pipeline to send earlier log messages. Log batching improves the way that we handle incoming log entries. Normally, you might want to write every log entry to disk immediately upon receiving it. However, this is expensive because you incur I/O overhead for every single log entry. Rather, you can batch log entries and write them all to disk right before the next heartbeat. Of course, this means that you might lose log entries because they're only kept in memory. However, log entries lost on a failed leader in this way are generally those log entries that would not be fully replicated and lost in the first place. One other category is failure tolerance. And this involves gracefully handling failures and the side effects of these failures and efficiently replacing failed replicas. Leader caching and request redirection is one way we achieve this. When a replica of our cluster fails, the leader changes. Raft requires that we send all of our requests to the leader. While Raft always makes sure to expose who the current leader is as long as the local partition knows in an ETS cache. So we always know the leader on the node that is hosting the Raft cluster, but this doesn't help remote requests. So when issuing remote requests, it's a good idea to keep a local cache of which node was the last to successfully make a request so that you can send it to that node again. If the request ends up on the wrong node because of a failure, it can be redirected to the correct leader At WhatsApp, we actually take the request and send it to the correct leader immediately without returning an error code. Once the request is processed by the leader includes information about itself in the response so that clients can update their caches in real time. Sometimes you might lose a whole replica. It might be irrecoverable. So in Wraft, replicas that have lost all their data start in a special stalled state. The stalled state is a state that does not participate in any quorum decisions because the follower could have had state that is important to some of these quorums. It could be one of the 3 members that are enforcing the most recent quorum. When a leader detects a stalled replica, it will transfer a snapshot of the entire state machine. Usually this snapshot is much smaller than the entire history of the state machine, so that it can bring this stalled replica back to a follower. This is safe because the leader is always guaranteed to be elected from the quorum, the most up-to-date quorum. So it is guaranteed that the leader's state is at least as up-to-date as the original followers. Critically, this removes our final dependency on the entire log. So we can start deleting the oldest portions of the log because we no longer need them. Multiple transport is not related to Raft, but it is one of the other ways that we've increased performance. Multiple transport involves using multiple network connections to increase network throughput and reduce network interruptions. In dist, a connection between 2 nodes consists always of a single TCP connection. To avoid head-of-line of blocking in dist, when you send a message, especially a large message, it may be multiplexed by breaking it up into small messages. When there are a lot of large messages in queue, it may take a very long time for a single large message to make it through. The time taken is proportional to the number of messages queued. At high levels of throughput, a random loss can cause a significant reduction in throughput over a single TCP connection while the connection stabilizes. So at WhatsApp, we use separate TLS connections for every single cluster that is running on every single Raft cluster that is running. A failure in a single TLS connection or TCP connection that is due to random frame loss or other truly random behavior is unlikely to affect other connections. And so we can maintain throughput even if a single cluster has trouble. As I described previously, completely lost replicas need a full snapshot of the database. However, databases can get very large. So the throughput of a single connection can be limited by the rate at which a scheduler can push bytes down it. So, and using dist to transfer the snapshots can lead to competition, as I mentioned. So at WhatsApp, we use, once again, multiple TLS connections to send the entire snapshot using Erlang and multiple schedulers so that we can get the stalled replicas up to speed as fast as possible. So these are some of the ways that we push Raft closer and closer to its limits. So how to start with Wraft? Wraft is available on GitHub. The link will be visible later. But it's designed to be very simple. Start with some options. You pass it, you get a child spec, and you can start it under your favorite supervisor. To get this cluster started, you figure out which nodes are part of the cluster, and then you make a config and you promote one of the members of the cluster to leader. This will become the first leader ever of your Raft cluster. Now you can start making requests. I have an example request here because your database will be different. And you can commit that to the database. And once you get this OK back, that means it's committed, it's been replicated everywhere. You're guaranteed that your log entry never changes. And that OK is very secure. You'll learn more here at that GitHub link. Thank you.
Yeah. It's still impressive after all these years that how WhatsApp continues to add to our ecosystem. So thank you very much, and thanks for representing WhatsApp to give us a new tool. Is there any questions in the audience for Henry?
So you showed the multiple TLS connections for handling, obviously, shaky TCP or large messages formats. Has WhatsApp been looking at all at something like Quick or something like that?
We did consider using transport protocols with built-in multiplexing and the ability to use potentially multiple sockets as a single logical socket. A lot of the difficulties were that if we were to adopt such an idea, such a protocol, we would like it to be part of dist itself, so that so that it could be used more generally. Implementing multiple transport over multiple sockets was really a last effort, or like best effort in the face of a lot of different options, so that we could get it out quickly and with as minimal future maintenance costs as possible.
Yeah, two questions. Regarding the replicas, the partitions of your replicas, how are you deciding and via which metrics are you deciding to partition those replicas? And do you also replicate them over geographic zones or just within the same geographic zones?
Because WhatsApp's database, so Raft is used generally at WhatsApp to store highly sharded, basically inherently sharded databases. Like our message database, the messages for a particular user are inherently separated from the messages for another user. And so sharding the way that, and this has to do a little bit with Ziu's talk yesterday, but this is the database he's talking about when he says millions of shards. Users' phone numbers are hashed. They're hashed to produce millions of microshards, which are then grouped up into shards that each of the clusters handles. And generally, the only heuristic we use to determine how many users should be assigned to each database is how much CPU each node is using.
We have another question from the online folk. Can you briefly discuss the pros of Wraft over RA or RA?
So, frankly speaking, I am not very familiar with RA. I'd say that, actually, I'm not familiar enough with RA to be able to answer that.
That's a good answer. Everyone take note. Any other questions before we wrap up? Excellent. I like that.
On the batching, I noticed so you had multiple logs, 1, 2, 3, 4, 5, and then that could potentially be passed out to all the followers. Is there some type of idea of like entry A on the state machine is going to be a put of key A to value 10, and then submit entry B is key A reverting it back to its original value? Is there any idea of reducing entries being added to followers?
So as of right now, there is no way in Raft or in Wraft to rescind a previous log message that you attempted to commit. In reality, for real database implementation, I would suggest that A, B, C, D here be actual transactions. So the contents would not just be, put some value in some key and here put another value in another key. They would be, update all of these different keys at the same time.
I guess just one more question onto that. It kind of, I guess, goes back to the idea of a rollback strategy, or what would be a rollback strategy utilizing Raft. I think that's kind of where my thought process was going to.
There is a lot of literature, and this would fall under in the realm of two-phase commit. And there is a lot of literature out there about two-phase commit. At the current moment, Raft doesn't provide any support for implementing two-phase commit.
Yeah, hello. So yeah, it's not as much as a question, more an answer. So we're using Henry's Raft at Cisco, and we also have like transaction layer above it with a two-phase commit protocol.
Have you guys run into any pathological situations around leader election where they just can't come to a consensus on who the leader should actually be?
So there's actually a little bit of a funny story here where, as you can see in our diagram, or in the diagram I prepared, like we distribute the Raft clusters over multiple nodes, but in Raft, the leader is doing all of the work, right? And so you would ideally want to balance the number of leaders on this node with the number of leaders on that node. Originally, the way we did this was by resigning leadership randomly on nodes that had too many leaders. This did not work very well, and at the point, it was a very good experiment because we did discover a lot of these pathological situations where, I would resign and nobody would become leader because, we're doing a deploy, so the node that could become leader is gone. In general now, now we avoid that because Raft implements the ability to hand over leadership gracefully. Yeah. While Raft, we also implement witnesses, and sometimes witnesses can also exacerbate this problem. Witnesses are copies that don't actually store any data, and sometimes they cannot be available. Oftentimes, we haven't really thought of a very good solution to avoid this. Oftentimes, this comes down to I have to go on these machines and tell it stop being leader, or you are actually now the leader, and make the decisions for it.
Hey, great presentation, very nice. So my question is, given that it's agnostic of the state machine, so it could be even something different than a database, right? How do you deal with this interface to make it agnostic, or what do you do actually? Like what strategy you chose to make it agnostic?
So, in a sense, I think I mentioned this on this slide, but when you have requests, we expect that you have some front code that converts the request into the log entry, and the log entry will travel through the entire Raft unchanged until it gets to your state machine in which you can consume it.
Well, Henry, I think we can all come to consensus that you did a fantastic job telling us about Wraft.